though other semiconducting materials are available. Silicon has the symbol Si and an atomic number of 14. This means that silicon atoms contain 14 electrons. 2 in the first shell, 8 in the next, then 4 in the outer shell. We refer to these outer electrons as valence electrons. These are the electrons which can form chemical bonds. Now we'll simplify our model of the silicon atom to show only the 4 outer valence electrons which take part in bonding. In individual atoms, the electrons can only occupy valent bonds with the neighbouring atoms. Now, out of interest, the diagram on the left shows what's known as the semiconductor bonding model. At 0 Kelvin, all of the outer electrons are bonded. The diagram on the right shows the energy band model. In order to explain the electrical properties of semiconductors, we only need to consider 2 energy bands, the valence band and the conduction band. These are separated by a band gap, which we'll discuss later. What I've not mentioned yet is that this is an undoped semiconductor of pure silicon, what we call an intrinsic semiconductor. As I said before, at 0 Kelvin all the outer electrons are bonded. Let's look at what happens when we add some heat. So, an electron has gained enough energy to break the covalent bond and is now free to take part in conduction, meaning that the resistance of the material is reduced. The absence of the negatively charged electron in this position leaves behind a net positive charge, which we call a hole. In terms of energy bands, the electron, which was initially in the valence band, jumps to the conduction band, leaving behind a hole in the valence band. The band gap, or energy gap, is just the energy required for the electron to break the covalent bond and jump into the conduction band. As the semiconductor is further heated, more covalent bonds are broken, resulting in more electrons jumping to the conduction band, with more positive holes created in the valence band. So as the temperature of a semiconductor increases, its resistance decreases due to the motion of the electrons in the conduction band and holes in the valence band. If we look at the diagram on the left, we can see that electrons from neighbouring atoms can move to fill a hole, leaving behind a hole in their previous position. Although strictly this was caused by the motion of negative electrons from left to right, we can also describe it as the motion of positive holes from right to left. Next, we'll look at energy bands in a little more detail. As I said before, we only need to consider the valence band and the conduction band in order to explain electrical properties of semiconductors, and for that matter, conductors and insulators. Remember then that in order for a material to conduct, it must have electrons which are free to move within its conduction band or holes in its valence band. In a conductor, conduction can actually be explained by considering only the conduction band. The conduction band is only partially filled, so electrical conduction is permitted. Unlike a semiconductor though, increasing the temperature of a metal conductor will actually cause its resistance to increase. This is because the number of electrons within the conduction band increases so much that they have less freedom of movement. Remember that in a conductor, the highest occupied energy band, the conduction band, is not completely full. In insulators, there's a very large band gap between the top of the valence band and the bottom of the conduction band. At 0 Kelvin, the valence band is completely full and the conduction band is completely empty. At higher temperatures, electrons don't normally gain enough energy to jump from the valence band to the conduction band. So with no electrons in the conduction band, conduction isn't possible. For an insulator then, the highest occupied energy band, the valence band, is full. Finally, semiconductors have a very narrow band gap between the valence band and the conduction band. Like insulators, at 0 Kelvin the valence band is completely full and the conduction band is completely empty. But since the band gap is so small, as temperature rises, some electrons can gain enough energy to jump from the valence band to the conduction band, leaving behind holes in the valence band. As temperature increases then, the resistance of the semiconductor is reduced. Next on the agenda is doping.